This video is a review of optics and light for AP Physics 2. I'd like to start by talking a little bit about the nature of light. We know that light is composed of electromagnetic waves, and that those electromagnetic waves are transverse waves. And we know they're transverse because the light is composed of oscillating electric and magnetic fields. And I'm attempting to show a picture of that in the top right corner. You can see that the electric fields and magnetic fields are oscillating in directions that are perpendicular to one another. And the directions of those oscillations are also perpendicular to the direction of travel of the light. And so all three of those things must be mutually perpendicular. Also, we know that because light is a transverse wave, that it can be polarized. And so if I have a polarizing filter or a grating that only allows light oscillating in a particular direction to pass through, then it can be polarized. And if I take two polarizing filters that have a common optical axis and I rotate one of them, or not a common optical axis, but a common transmission axis, and I rotate one of them 90 degrees, then light oscillating in either direction will be prevented from going through, and those two polarizing filters will together block all of the light. We know that mechanical waves, so not light, but other mechanical waves, things like sound traveling in air, or a wave traveling along a string, or a slinky, or a spring, that these things require a medium in order to travel. And so for sound, the air is the medium. Without the air, there can't be any sound. And for the string, or the slinky, or the spring, more clearly, you have to have those things present in order to carry the energy of the wave from point A to point B. However, electromagnetic waves can travel without a medium, which is important because it means that electromagnetic waves, light, can travel through space where there's no medium to carry the wave. And we know that in a vacuum where there is no medium, that the speed of light is equal to about 3 times 10 to the 8 meters per second. That's a constant that we should definitely know. We also learned that light has a characteristic wavelength that we represent with the Greek letter lambda. And it also has a characteristic frequency. And the product of frequency and wavelength are always equal to the speed of light. And so since the speed of light in a given medium is constant, as the wavelength increases, the frequency will decrease, or as the frequency increases, the wavelength will decrease. So there's an inverse relationship between that wavelength and frequency. Now, the speed of light is constant, but it doesn't have to be the same all the time. What I mean by that is, if light moves in a medium that's not a vacuum, whether it's air or glass or water, then light slows down. And you might remember us talking about optically slow and optically fast materials. And so when light moves into a medium that is more dense, it is more optically slow and the light slows down. And we're going to talk a little bit more about that later, but for now, please also remember that there are different regions of the electromagnetic spectrum that are identifiable, right? We talked about radio waves, microwaves, infrared waves, visible light, ultraviolet rays, X-rays, and gamma rays. And in principle, maybe we should remember the exact order of these just for convenience. But I think most importantly, we should remember that radio waves have a very long wavelength and a low frequency, and because of that they have low energy. And gamma rays have a very high frequency and short wavelength, and so they have a lot of energy. And that's why things like gamma rays and X-rays are more dangerous for human beings. Because of their more energy, they interact with tissues a little bit differently and are more dangerous for us. Also remember the order that the colors go in the visible part of the spectrum. The red light has a longer wavelength, lower frequency, and the blue light has higher frequency, shorter wavelength. We also learned that light can be modeled with an equation that involves a sine or a cosine term. And that's because light is wave-like, and it's its electric field is oscillating as a function of time, for example, and so the wave could be graphed to look like a sine or a cosine function. Now my equations here say cosine, but in my graph I suppose I started it at 0, and so maybe they should say sine. But regardless, I can write an equation for the electric field as a function of time, where A is the amplitude of the oscillations, omega is the angular frequency, which is related to the period and the frequency with the equation given below. Or I could substitute in 2 pi f instead of writing angular frequency and get the same exact equation from the manipulations down below. But bottom line, this equation tells me that as time moves on, the cosine function changes and I get different values of the electric field. If I look at a graph, other than the amplitude of the oscillations, I can also get the period very easily. Right? The period would be the amount of time between two successive peaks, or two similar points on the wave. Which means that if I know the period, then I can find the frequency, and I can pretty easily substitute in all the values into the equation. As we were studying light this year, we learned that light is a wave, and if we want to understand how light behaves when it's in the vicinity of other light waves, so when those light waves start to come together, when they cross paths, when they interfere, then we need to understand how things interfere in general. And in those cases, we learned of two different types of interference: destructive interference and constructive interference. So first off, when I have two, and now I'm up here in the top left-hand corner, when I have two wave pulses that come towards one another, so maybe just we're looking at a string or a spring where somebody's created a wave pulse. When those two wave pulses are traveling toward one another, and one of those wave pulses maybe has a positive amplitude and the other one has a negative amplitude, so they're on opposite sides. When they meet, they will destructively interfere because the sum of the amplitudes of those two waves, the top one positive and the bottom one negative, will cancel out and be 0. And momentarily it'll look like there's nothing there, and then, because of conservation of energy, the wave pulses will continue on in the same direction that they were traveling in before. And so that means B, which was on the bottom, is now on the left-hand side, and A, which was on the top, is now on the right-hand side. They continue to move in the direction that they were traveling in initially. And the only other thing that can really happen is if C and D, these two wave pulses in the second case, are both on top, so they both have maybe some amount of positive amplitude. When they meet up, because their amplitudes are on the same side, the amplitudes add together and we get a larger amplitude. But once again, after they overlap, the superposition of those waves gives us that bigger amplitude. But then after then, wave pulse D is now on the the left-hand side, and wave pulse C is on the right-hand side, which means those wave pulses continued to move in the same direction. What's important here is for light, what this means is when we have constructive interference, there's going to be bright spots, and when we have destructive interference, there's going to be dark spots. One of the most important experiments of the last couple hundred years is the double slit experiment. And one of the reasons why it was so important is because it proved the wave-like nature of light. On the left-hand side of this diagram that I have drawn here, I have red light that's coming in, and it's going to go through a couple of slits. And what we observed is that when the light passes through the slits, there is interference between the light coming through the top slit and the light coming through the bottom slit. Because of that, in some locations there's constructive interference, in some locations there's destructive interference. And so on a distant screen, we observe some places that are bright. These are the places where I have these large amplitudes. In some places it's dark, like in this location here. And then again bright, dark, and then bright. And so what we're observing are places where there's constructive and then destructive, constructive and then destructive interference. That constructive and destructive interference occurs in places where the amplitudes either add up or they subtract. And what we found is that there's a geometric relationship between the location of each slit and a corresponding point on the screen where at some locations the difference in the path length, and I've shown this in yellow, the difference in the path length between the two is equal to one whole wavelength or equal to 1/2 wavelength. One of those two criteria are going to determine whether we get a bright spot or a dark spot. What I mean by that is maybe for the two blue lines that I've drawn to that particular point on the screen, the difference in the path length is exactly equal to one wavelength. So delta L equals one wavelength. And what that means is exactly one wavelength will fit in this region where delta L is drawn here in the diagram. And for that reason, when the waves get to the point on the screen where the light could be piling up there, what will happen is there's going to be a bright spot because the two waves will be in phase when they arrive there. And they're going to be in phase because the difference in the path length is exactly equal to one wavelength. Now, higher up on the screen, there's going to be another location where the difference in the path length was exactly equal to 2 times the wavelength. And so I suppose here this should say 2 lambda, not 2L. And so at any location where the difference in the path length is some integer number of the wavelength, there will be a bright spot. And that's my first bullet point down below. Differences in path length of some integer number m times lambda are places where there will be constructive interference or dark spots. And then obviously, if they're in phase when the difference in the path length is equal to 1 lambda or 2 lambda, 3 lambda, then the way that I would get destructive interference is if one wave was like halfway out of phase with the other wave. And that would occur when the difference in the path length between the two slits to the screen is some half integer multiple of the wavelength. So if m is still some integer multiple that's 1, 2, 3, I would have to add 1/2 to that to find all of the half integer multiples of the wavelength, which would mean those would correspond to the places where there's a dark spot. So that's a lot of information. In general, I think we need to remember a few things. One, the central maximum will be a bright spot with the greatest intensity. As I move away from the central maximum, the intensity of the light is going to drop off. There's going to be bright spot, dark spot, bright spot, dark spot. Those spots correspond to places of constructive and destructive interference. And the equation that relates these variables is on the right-hand side, where d represents the distance between the two slits. Theta represents an angle relative to the central maximum from each slit. And here, since the screen distance has to be large in order for the diffraction to occur, since the screen distance is so far away, those two angles from each slit up to a particular point are equal. M represents the order, the integer locations where the constructive interference occurs, so the bright spots. And if we replace m with m plus 1/2, we get the dark spots. And lambda represents the wavelength of the light that was incident on the two slits. The last thing that I'd like to remind you of is that in order for the diffraction to occur, the wavelength of the light must be on the order of the distance between the two slits. Or perhaps more importantly, the distance between the two slits needs to be on the order of the wavelength of the light. Now, a separate phenomenon that we observed is that when light travels from one medium to another, some of that light gets transmitted, it means it goes through, some of it gets reflected off the surface, and then some of it gets absorbed. And one of the more important properties of light that we studied was the property of refraction, which means that when light passes from one medium into another medium that has a different index of refraction, then the light can bend. And that bending occurs at the boundary between the two media. And there are a few things that we need to remember. First, different media, so air, glass, vacuum, has a different refractive index. And the refractive index, which I've shown on the left-hand side here, is the ratio of the speed of light to the speed that it travels in a particular medium. So for example, in a vacuum, the speed that it travels is the speed of light, c. And so c divided by c gives me 1. So for a vacuum, n is equal to 1. But in something like air or glass, the light will not travel as fast, which means that v is a little bit smaller than c, and so the refractive index will be greater than 1. And so for anything that's not a vacuum, the index of refraction is greater than 1. And in general, there's kind of like two cases to this. If I'm moving from an optically fast material to an optically slower material, which means that n1 is less than n2, then the light will get bent closer to the normal. So please remember that the dotted line that I have drawn in these pictures represents the normal, which is perpendicular to the boundary between the two surfaces. And theta 1 and theta 2 are always measured with respect to the normal. And so when I say that theta 1 is greater than theta 2, I'm saying that the light is getting bent toward that normal line. And then the other case is when the light passes from an optically slow to an optically fast medium, then the light will get bent away from the normal, which means that theta 1 will be greater than theta 2. Theta 2 will be greater than theta 1. And all of this information, luckily, is contained in Snell's law, which says that n1 sine theta 1 equals n2 sine theta 2. It's really important, however, that we remember that when it goes from a fast material into a slower material, it gets bent toward the normal, and when it goes from a slow material into a fast material, it gets bent away from the normal. Another phenomenon that we talked about when we were learning about refraction was the idea of light being internally reflected due to it being beyond the critical angle. So in my diagram down below, I have a boundary that's there between some glass and some air. And what we learned is that if I am having light move from an optically slower material to an optically faster material, right? The light moves faster in air than what it does in glass. Then n1 is greater than n2. And when n1 is greater than n2, and I put the light incident at theta critical, the critical angle, then what will happen is the light will go down to the boundary and it will be reflected, or rather than that, skim along the surface. And that's what I'm saying at the bottom there. At theta critical, if I have light coming in at an angle, that's the critical angle, the light will get bent and go along the boundary between the two surfaces. And if I make theta any bigger, right, so theta critical represents this angle that I'm drawing in green. If I make theta any bigger, so for example, this ray that I've drawn here that's in yellow, if I make theta any bigger, then all of the light will be totally internally reflected in the glass, and none will go into the air. And so we need to think about why this happens and how that fits in with Snell's law. So what we do is we write Snell's law, n1 sine theta 1 equals n2 sine theta 2. And we solve that for theta 2. The angle that the light should be making with respect to the normal in the air in this case. So the angle that should be occurring down here. And what we find is that if n1 is greater than n2, then this fraction, n1 over n2, is going to be greater than 1. Which means that sine theta 1, if we start to make theta 1 large, then eventually sine of theta 1 is going to be a pretty large number. And when I multiply that by a number that's greater than 1, then there's the potential for the right-hand side of that equation to be greater than 1. And sine of theta cannot be greater than 1 because sine of theta has a maximum value of 1. So let's reiterate that. I have that down in blue. Since n1 is greater than n2, when theta 1 becomes large, sine of theta 2 would need to be greater than 1, which is not possible. And so, therefore, we should be able to solve this equation for theta 2, where theta critical is the value of theta 1 for which theta 2 is equal to 90 degrees. So what theta critical represents is some value of theta 1 that when I plug in that value, theta 2 needs to be 90 degrees. In principle, I think if you were asked to find the critical angle, just let theta 2 equals 90 degrees and solve for theta 1. And that angle is going to be the angle at which the light would skim along the surface. And if you make the angle any bigger, it's going to be internally reflected. If it's any smaller than that, we still get refraction in the same way that we had before. Now I'd like to change topics a little bit and talk more about mirrors and lenses. So first we're going to talk about flat mirrors. When light hits a smooth reflecting surface like a flat mirror, it reflects at the same angle relative to the normal. So here we call these incident, and reflected angles. And for a flat, smooth surface, all of the light is going to get reflected at the same angle that it had when it was incident on the surface. And remember, again, those angles are measured relative to this normal line. Also, when I have a mirror, all of the images formed by that flat mirror are going to be upright, virtual, and the same size. And maybe you remember that means our ray diagrams are pretty simple. So if I place an object like an arrow on the left-hand side of a mirror, when I draw a ray diagram to figure out what that image looks like, I would typically select a point, I would draw one ray that goes directly toward the mirror, and then I would draw one ray that goes at some arbitrary angle toward the mirror. I would then identify what the perpendicular line looks like, the normal line. I would then draw a reflected ray that goes away from the mirror at the same angle that it was incident on the mirror. And then I need to trace these reflected rays back into the mirror. So for example, the reflected ray for this one at the arbitrary angle is like this, so I would trace it back like this. For the ray that goes directly toward the mirror, it will be reflected directly straight back. And so that reflected ray will be somewhere like right there. The place where those two rays cross is the location of the tip of this arrow that I drew, because that's where I was drawing the rays relative to. Therefore, I now know where my arrow is. And if you notice, if I had done that a lot more carefully, the image would always be upright, it would always be virtual, which means it's in the mirror, and it would always be the same size as what it was originally. So the more careful you are, the more true that those bottom statements would be, which means no matter where I place the image, no matter where I place the object, we should get an image that obeys all of these rules that we've said. Lastly, one thing that I did not mention is that this object distance is always going to be equal to this image distance for a flat mirror. And of course, when we studied curved mirrors, we found that things work a little bit differently, and there's a little bit added complexity. So first, let's talk about a concave mirror. And a concave mirror looks like the pictures that I have below. There's a focal point that's a little bit a ways away from the mirror, and there's a point which I've labeled C, which is called the center of curvature of the mirror. And for any concave mirror, that center of curvature point is always going to be equal to 2 times the focal point. Any light that is parallel to the optical axis and incident on a concave mirror will be reflected through the focal point. So regardless of where this parallel ray is coming in, the light will get reflected back to the focal point. And if I wanted to figure out where the image would be if I placed an object near a concave mirror, then there are 3 lines that I can draw, 3 rays for my ray diagram that I can draw in order to figure out where that image is. And so I have a picture on the bottom here of a little triangle, and there's a little dot at the top of that triangle, and I'm going to draw those 3 rays relative to that dot. First, I need a ray that is parallel to the optical axis but reflects through the focal point. So a ray parallel to the optical axis looks like this, and it needs to reflect through the focal point. So there's the focal point. So incident ray, reflected ray. The next ray I need to draw, ray number 2, is a ray that goes through the focal point but reflects parallel to the optical axis. So this would be a ray that goes through the focal point and through the point that I selected on the object, but then reflects parallel to the optical axis. The last point should go through the center of curvature and then reflect through the center of curvature. And so really I can only draw one ray here. It would be both coming in and coming out through the center of curvature. And what I can then do is take the reflected parts of each one of those rays. So we should be imagining a ray that's right about here. That's one of the reflected rays. A ray that is right about here. Okay. And then lastly, a ray that's coming up something like this. Alright, so each one of those reflected rays gets traced back into the mirror, and it can help me figure out where the image is going to be. Now, I've done a particularly poor job of drawing this ray diagram. I've done a poor job because I've not used a ruler, and the ray diagram is relatively small on my screen. And so for that reason, all three of those reflected rays do not converge at a single point. But you can see pretty clearly that a couple of those rays I drew decent enough that the point on the triangle can be drawn on the right hand side. And maybe if I had drawn a more realistic diagram, then that third ray would have converged to the same point. And it's where those rays converge that you know that dot is there on the other side. And so now I can draw in the rest of the triangle. And what I observe about the image that I've just drawn is that, okay, the object was within the focal point, and the image that I got was upright. It was virtual because it's in the mirror, and it's magnified larger. Also, the image distance is greater than the object distance. And maybe that was poorly indicated because of my fairly sloppy drawing, but the image distance should indeed be larger than the object distance. And so this is for one example of a concave mirror. And what happens with a concave mirror at the focal point, within the focal point, outside the focal point, outside the center of curvature, it's actually pretty complicated because in each case we get something a little bit different. And so, but in principle, if you remember how to draw those three lines, then you're in good shape, because then you can always figure out what the image looks like. Now let's look at an example of a convex mirror. So for a convex mirror, we used the same three lines that we drew for the concave mirror, but the only difference is the focal point and the center of curvature are on the other side of the mirror. And so the way that this works is first I'll draw a line that goes parallel to the optical axis and then reflects through the focal point, something like this. And then I'm going to draw a ray that would go through the focal point, maybe something like this, but it needs to reflect parallel to the optical axis after it goes through the mirror. So I need to draw that line again and have it go incident on the focal point, but then when it gets there, it needs to reflect parallel to the focal point, something like this. And lastly, I need to have a ray that goes from the tip of the object straight through the center of curvature and then reflects through the center of curvature, so the line can just go straight through. And maybe you can see that all three of those lines are converging at a particular point there. And the first bullet point that I have below says that for a convex mirror, the image is always smaller, it's always virtual, and it's always upright. And that seems to be fairly consistent even with my pretty quick ray diagram that I've drawn there. And the image is always within the focal point, which is consistent with my ray diagram. So again, I draw the three rays, and I'm able to figure out where the image is. And I'm able to use words like smaller, bigger, virtual, upright, inverted, and talk about its location. But as I said, for a concave mirror, my second bullet point, it's going to really depend on the position of the object. So is the object in a position that's greater than, equal to the focal point, or is it greater than twice the focal point? And I suppose I wrote the same thing on there twice. One of them probably should be less than. Um, my suggestion to you for that is to just go ahead and go to ophysics.com, where we've seen a great simulation for looking at flat mirrors and curved mirrors in order to understand how the object and the image are related to one another for different positions and different types of mirrors. In principle, I think the last thing that I would remind you of is that you can always just take those 3 lines that we talked about to find where the image is and then talk about the image yourself. So remember, one line is parallel to the optical axis, reflects through the focal point. One line is going through the focal point and reflects parallel to the optical axis. And the third line goes through C and reflects through C. For doing calculations with mirrors and subsequently lenses, we've mainly used 2 equations. The top equation relates the image distance, object distance, and the focal length of a mirror. And if you know what the image distance and object distance is, then you can find the focal length, for example. Or we did in a lab in class where we plotted 1 over the, I believe it was the image distance versus 1 over the object distance, and we were able to determine the focal length from the x or y intercept on this graph. And so this equation can be linearized to find the focal length if somebody does multiple trials of measuring the image and object distance in an optics lab. And the second equation was an equation for finding the magnification of an object, whether it will be larger or smaller, which is a unitless number. And if the magnification is equal to 1, that means that the object and the image are the same size. If it's larger than 1, that means the image is larger. If it's less than 1, the image is smaller. And you can figure out the magnification using the image distances or, the image and object distances or the image and object heights. And lastly, for these equations, it doesn't really matter what units you use as long as the units you use are the same for each term in the equation. So if you want to find the focal length in centimeters, just measure SI and SO in centimeters. The last thing that I'd like to do is talk about the 2 types of lenses. There are converging lenses and diverging lenses. Converging lenses take all the light that's parallel to its optical axis, and they converge the light to a single point. We call it the focal point. And a diverging lens, which looks like the lens down below, takes all light that is parallel to the optical axis and diverges it, spreads it out on the other side of the lens. But what is true is that all of those diverging rays, if you trace them back, reflected those rays back to the left-hand side of the lens, they would all converge into a focal point. And for that reason, we know that for a converging lens and a diverging lens, the focal points are on different sides of the lens. And so they work differently, but there are also some similarities between the lenses that we can use to understand how they work. In talking about lenses, there are just a lot of different things that could be mentioned. And so here I'm going to have about, I think, 5 or 6 slides, which are going to take us through different cases of the object and image positions. And there's a lot of things that I'm not going to mention, but these are things that you could read on the screen about the different instances. So first, let's talk about this first one a little bit. Here I have a converging lens, which converges light to a single point. And what I notice about this is in this ray diagram, I can draw a line that is parallel to the optical axis and reflects through F. I can draw a line that goes directly through the center of the lens. That's shown in blue. And I can draw a ray that goes through the focal point and then reflects through the lens and then is parallel to the optical axis. And those 3 rays converge at a single point, and that is the location of the similar point on the object for the image. And what we see here is my object was outside twice the focal length of the lens, and my image was inverted, it was smaller, and it was had a magnification less than 1 because it's smaller, and it's real. And the reason why the image is real is because the rays go through the image. If the rays that produce the image were reflected rays, then the image would be virtual. Think back to a plane mirror. In order to form the image produced by a plane mirror, you have to take the rays and reflect them back into the mirror. We call that a virtual image. Here the image is real because I'm taking the physical rays and forming them into the image. Now I've moved the object to at 2f, and I notice that the image is still inverted, and everything else is pretty much the same, except for now at 2f, I notice that the image and the object are exactly the same size. And so maybe this is something worth remembering. At twice the focal length of a converging lens, the image and object will be the same size. Now I've moved the object to be within f and 2f, so greater than f but not as great as 2f. Here I notice that the image now has become larger, but it's still inverted and outside the focal point on the other side. The image is still real because the rays are going through the image and it's behind the lens. The moment I take the object and put it within the focal length of a converging lens, then the image is no longer on the right-hand side of the lens. The image is now virtual, which means that in order to produce the image, I would have to take reflected rays and intersect them. Notice how the ray diagram looks a lot more complicated, but I'm still drawing the same rays. So notice the green line. It's parallel to the optical axis, and then it reflects through the focal point. And that reflected ray gets traced back to the image. Look at the blue line. The blue line goes directly through the center of the lens and gets reflected back directly back to the image. The yellow line goes through the focal point and then reflects parallel. And all three of those rays converge at the tip of the image, and I notice that the image is upright now. It's larger than the object, which means the magnification is greater than 1, and it's virtual because the image is produced by reflected rays. The very last ray diagram that we need to look at is the ray diagram for a diverging lens. And for a diverging lens, there's really only one type of ray diagram. For a converging lens, we saw that there's different things going on at different locations, but for a diverging lens, it's pretty easy. So first, I draw a ray that's parallel to the optical axis. It reflects and goes through the focal point. That's the green line. I draw a ray that is incident on the focal point, but then reflects parallel to the optical axis. That's the yellow line. And then the blue line goes through the center of the lens and then comes right back the same direction. And all of those rays converge at the image. And what I notice is that the image is always going to be upright. It's always going to be smaller than the object, which means the magnification is less than 1. And it's always going to be virtual because the rays don't go through the image. It's reflected rays that get traced back to the image. And so for a diverging lens, the ray diagram always looks something like this. Although as you move the object around a little bit, the image will get smaller or bigger, but it will always be smaller than the object and appear in the same way as what I've shown here. I think my biggest piece of advice would, again, maybe to just go to ophysics.com and check out their simulation, because the simulations under the light category show you for all different types of lenses and mirrors. They allow you to drag the object back and forth and look at the images and get a better sense of how the lenses and the mirrors work more intuitively.